Welcome to the Chemically Dope podcast by AIChE-VIT, where we dive into the world of chemical engineering and connect with professionals, students, and chapters across the globe. In season 1, we invited esteemed professors to share their knowledge and deepen our understanding within the realm of chemical engineering, while in season 2, we are bridging continents by interacting with AICHE student chapters worldwide. Today, I, Adya Saxena, and Shagnik will be your hosts, and we are glad to welcome respected Dr. Samarshi Chakraborty, who will share his insights, experiences, and perspectives on the dynamic field of nanofluids. Welcome, sir, to the podcast. We are extremely grateful to you for giving us your precious time.
Thank you for having me. It's been a privilege that you people asked me to join for this podcast. I thanks all the coordinators and organizers for having me in this program.
Yes, sir, we are grateful to have you here. So, before we go on to the podcast, let's introduce our guest. Dr. Samarshi Chakraborty, currently working as an assistant professor at BITS Goa, is an accomplished postdoctoral researcher with a PhD in chemical engineering from IIT Kharagpur. With expertise in AutoCAD, Aspen Plus, and management, he has made significant contributions to higher educations and nanofluid research. His recent collaborative study, published in the Journal of Molecular Liquids, focused on optimizing heat transfer performance of mono and hybrid nanofluids. Ranked among the top 2% of researchers globally, Dr. Samarshi continues to impact the field through her scholarly work while serving as a review editor for Frontiers in Thermal Engineering. So, now we'd like to continue the podcast by asking you a few questions related to your field.
Good evening, sir. It's wonderful to connect with you. So, nanoparticles is something that we read about and we get to know about a lot in scholarly discussion and even in classrooms where most of our professors tell us about this dynamic field. And so, we wish to know more about nanoparticles, and for that reason, we are very glad that you're here. I had read somewhere that nanoparticles have a tendency of enhancing the thermal properties of fluids. So, I wish to ask that how exactly does this work out?
To be very precise, to understand the field of nanofluids, first of all, we must understand how a fluid should operate. Fluids, basically, when we talk about any cooling fluids, so the best fluid that is given by the god or by the nature, I would say, is uh, water. Water has the highest thermal conductivity among all known conventional fluids that we know of, in compared to refrigerant, alcohols, organic liquids, biofluids. So you name it, water has the best thermal properties. But now, what is the problem with water? The problem sometimes becomes with water is that it does not perform very well when we are operating at a very low temperature, and where there is certain restriction related to, let us say, some thermal conductivity. So if I want to cool down your, let us say, your laptop that you are currently using, so if I spray water on it, the circuits are going to explode, right? It's going to short circuit is going to happen, it's not going to work out. Now, the challenges that the field of like thermal engineering, and specifically the field of coolant development, there is the major problem is that we cannot improve the thermal properties of water. So generally, water has a thermal conductivity of around 0.58 to 560, like 0.58 to 60 watt per meter Kelvin in room temperature. Yes, you can increase it if you operate at a high temperature, but that I will keep it out of discussion for now. Now the challenge is that we everybody knows that solid is a better conductor of electricity as well as heat when compared to any fluid. But you have to understand that when we mix solid into a fluid, what happens? I'm not talking about something that is dissolvable. I'm not talking about salt, or I'm not even talking about sugar. I'm talking about something which can be suspended, not soluble in it. So what happens when we are adding certain particles into the fluid? It has a normal tendency to destabilize. Now the question is, why it destabilizes? So the fundamental problems that happens is that there is van der Waal attractive forces which are acting on the particles, which make the particle to agglomerate together in many ways. And then what happens, it basically forms a larger cluster, and because of the gravity it settles down. Now the question comes, why we are actually going for developing nanofluids? Why not even microfluids? And let us say I can understand millimeter size fluids doesn't work out. Now why microfluids or like micron size particles we are not suspending? So that has been seen that in repeated studies, that even if you are using micron size particles, what happens over a period of time, because of the presence of the van der Waal attractive forces, what happens, the particle tends to agglomerate and tends to, I would say, sediment onto the surface. So if I am saying that I am using it for cooling certain surfaces, if the heat is given to the fluid, generally what happens? So you are providing not only heat to the fluid but also heat to the nanomaterial as such. So when the heat is provided onto the nanomaterial, what happens? That nanomaterial's movement, the interaction becomes even more vigorous. And because of that interaction, what is happening? More and more particles are coming in contact, and because of the van der Waal attractive force, sometimes it forms a cluster even faster. So that is why you might have heard about some advanced heat transfer devices like microchannel heat transfer devices, microchannel heat exchangers, like heat pipes. So on those type of systems, micron size fluid particle does not work out. And to enhance your thermal properties also, you need to add, I would say, around 10% and sometimes even 20% of the particles to have a, let us say, standard enhancement of around 10 to 20%. But if you add that much amount of materials, what happens? You are basically making sure that the material gets destabilizes very quickly. So that is where nanofluids comes into the picture, because of its very small dimension. So what is nanofluids? Nanofluids is basically one of the dimension of the nanoparticle must be below 100 nanometer, then only that fluid or that suspension we can call it. So you can use water, you can use alcohol, you can use oils, you can use refrigerant, whatever base fluid you can use it, but the dimension of the nanoparticle has to be less than 100 nanometers. And then when it is added into my system, what happens? The question is the mechanism behind it. The mechanism, the most relevant mechanism, people have said that it is Brownian motion. So your solvent particles are basically kicking off the uh, nanoparticle suspended in it from one place to another place, and because of that movement, random movement of the nanoparticles, your heat transfer becomes better. Now the I have talked about the problems associated to the clustering or agglomeration. But here what happens, nanomaterials, even when it clusters, it generally may be forming like a little bit on the submicron level clusters. So in that submicron level clusters also, sometimes what it does, it actually creates a conductive pathway. So you know that I have told you at the beginning. So conductive pathway of the solid can actually transfer heat in a much more like a easier way compared to any fluid. So if that conductive pathway is there, so it will transfer the heat very effectively. Then also another phenomena is there, how the fluid is actually behaving when it's coming in contact with the nanoparticle. So there is a concept called liquid layering or interfacial layering. So what happens, around this nanoparticle, the liquid will layer itself in such a way that it will have a very good ordered structure. So the bulk fluid and the liquid which is layered surrounding the nanomaterial would be such that that layered or that more structured or more ordered liquid are provides better conductive pathway for the nano particles to interact, and thereby complements to the thermal conductivity. There are other mechanisms such as microconvection, thermophoresis, like optimum clustering. So and obviously, and the one of the biggest part is that obviously the nanomaterials have higher surface to volume ratio, and because it has higher surface to volume ratio, naturally it is expected to show better heat transfer performance, better thermal conductivity compared to any micron size or even normal like only the base fluid. So this is, I would say, in a nutshell or in a elaborative way, you can say how the mechanism works out and how it differs from the normal conventional micro level micron size fluid particles as well as conventional base fluids.
Okay, thank you, sir. That was a really good explanation. Now, as you said that in a extremely detailed way, that nanofluids, they have been getting attention for their ability to improve heat transfer in the industrial systems. But while this sounds promising, I wanted to ask if are the nanofluids currently economically feasible for large scale industrial use, or is maybe further development needed to reduce the costs which can be incurred in this? And can they be actually a viable solution for improving energy efficiency?
To answer that, first of all, I must say that I am also a part of the problem and I'm also trying to solve the problem. So I would say that the field of nanotechnology is has immense promise. So there is no doubt about it, the nanotechnology can change the face of the earth. But the problem is with the cost of making nanomaterials. Until and unless, I think you most of you might have heard about a material, wonder material called as graphene. It has been developed in the year of I think 2010 around. So in Manchester, but you must also be knowing that even after 10 or around 14 years have passed, so till then we haven't seen too much of actual scale application or scalable production of those type of graphene based nanomaterial in an industrial scale. Because like when we are talking about scalability, we have to compromise with certain properties. When we are thinking about making certain nanomaterial in a pristine way, we have to think about, okay, if I use this chemical method or a thermal degradation or a chemical exfoliation, how we can do it. But the problem and the choice comes that whether we have to think about the scalability part, whether we are only concerned with the purity aspect. So there has to be a trade off. Now the problem with nanofluids is also the same. First of all, you have to develop the nanoparticles in a very cheap way, in a very scalable way. Until and unless you produce nanoparticles in kgs, in tons, then only the overall production of nanofluid can be reduced, because the nanoparticle itself is the main, I would say, the main role player in this nanofluid. So if I make the nanoparticle in a cheap way, use techniques. So there are actually two kinds of techniques. One is one step method in nanofluid synthesis, another one is two step method. Now in one step method, you prepare the nanoparticle within the base fluid itself. You don't actually prepare it, you separate the nanoparticle and then again you disperse it. So that becomes a two step method. Problem with two step method is their stability is the biggest problem, biggest concern. You cannot make those nanofluids remain stable for a longer duration. The challenge with this one step method, which I was actually advocating for, the problem is that it cannot be scaled up to a very significant high extent, so that I cannot produce in liters of those nanofluids, or let us say in much higher quantity. So if you cannot scale it up, then the problem, yes, the question that you have asked, that the economic aspect is there, but the advantage is that the existing nanotechnology, or I would say in the field of nanofluids, several works are being currently done to particularly tackle the issue of cost effectiveness. So there is a factor we always talk about. The factor is in nanofluids term is called as the price performance factor. What is this price performance factor? So price performance factor is your enhancement in the thermal conductivity should overpower the cost that is incurred by making the nanofluid. If that is less than 1, then making the nanofluid does not make any sense. So that is what we have to focus on. The researchers working in this field are actually working on to make sure that this price performance factor is always greater than 1. Then only using it makes a sense. And Obviously, if you are, even let us say, if I say that a nanofluid which you have, let us say, making a 1 liter of nanofluid might cost you, let us say, 10,000 for a discussion purpose, let us say, take it. But let us say if I'm able to reduce the energy consumption, how nanofluids plays in energy consumption reduction, because it has higher thermal property, so the energy efficiency of that system would be better. So even if the thermal conductivity increase by 10%, 20%, you can easily understand that's impact on the energy savings perspective. So in a long run, maybe the initial production cost is high, but if I consider the overall operational life of the nanofluid, the amount of energy that has saved. So energy saved means environmental impact that is reduced, because energy, how we are getting it, majority of the energy we are getting it from the fossil fuel sources. So our environmental impact is also significantly reduced. So we have to weigh in that over a period of time, even the initial cost may be a slightly high, compared to its overall life cycle, how much amount of benefits we are getting by paying that amount of money. So if that is justified, if that factor is justified, I told you about the price performance factor, then I would say that doing synthesizing nanofluids is justifiable, and then their application is justifiable. Now I think, coming back to one part I just wanted to add, in terms of this industrial applicability, maybe say, like why people should or should not use nanofluids at its original state, depends on what is the uh, amount of, what can I say, amount of energy consumption that goes into your system. If your system is highly energy intensive, then using nanofluids makes a lot of sense. If your system may not be highly energy intensive, then you may not actually go for it, because like, then obviously the cost may actually overpower the benefits that you are getting from the nanofluid. So those factors you need to weigh in, then only you can come up with a conclusive answer. Yeah.
Okay, so nanofluids certainly are, they have a lot of potential, but I wanted to ask that what are some underdeveloped areas that you see that have untapped potential or that could be looked into for further research?
uh, One field I do believe that nanofluids have been like over explored is the thermal application, thermal engineering application. Extensive work has been done. I don't have to tell so many papers, hundreds, I would say thousands of papers on a year basis, it actually gets published in this domain. But I would say that one field I do feel that nanofluids has an immense potential. I think in the field of energy, I would say energy harvesting, biomedical application. I will also say that in terms of like environmental remediation. Now where these fields are, I would like point by point I will focus. I would say that in terms of the biomedical application, so you might have seen that in chemotherapy, when a person is given a chemotherapy, generally when that chemotherapy is injected, you have a sense of like your entire body, good cells or the bad cells or cancer affected cell, basically overall gets affected. So nanofluid can be a tool actually to provide a excellent targeted drug delivery, hyperthermia treatment of cancer. So there is enormous applications that can be explored. I do feel that nanofluids, I would say nanofluids with a fluorescent, fluorescent nanoparticles, if you inject it, let us say, that nanoparticle will maybe only reacting where you might have a cancerous cell. So by injecting that nanofluid into your body, you can detect that yes, there is cancer that is growing in this part. So there are enormous amount of opportunity in terms of biomedical application. Yes, still it needs to be explored extensively. Another field I have also worked on a bit on this, that is like nanofluids potential to capture CO2. It is quite astonishing actually to say that. So the nanofluids, what it does actually, not only with the help of the base fluid, but because of nanomaterials, if you choose the nanomaterials particularly to capture CO2, which has a affinity towards CO2, or let us say greenhouse gases, so it can actually absorb more greenhouse gases for the, let us say in nanofluids, how much amounts we use in ppm level. So let us say point let us say 200 ppm or 0.05 weight percentage, which is like very negligible. With that very negligible amount of nanoparticles, nanofluids, you are able to capture, I would say, compared to a base fluid, CO2 capture efficiency can increase up to 70, 80. And if you tune the property of the nanofluid, it can even go beyond 1.5, 1.6 times. So which is quite incredible. So it's like, I would say, one of the untapped area that is there. I think more research is going on. I would say that the area which has like matured a little bit more, which is like energy harvesting potential through solar energy, because nanofluid has a excellent ability to absorb solar energy. And like the performance of the solar collectors can be improved by 20-30 percentage by using very tiny fraction of nanomaterial. So I think these are the areas further needs to be developed. There are more areas, but because of the time constraints I cannot delve into those parts. So in my opinion, these are the areas which needs like more focus to be given.
As much as we would love to continue this conversation, we are sadly out of time. Thank you so much for joining us today for this session, sir. And also a very big thank you to all the listeners of Chemically Doped for joining us on this session on nanofluids, heat transfer, and everything that it covers. Thank you.